Okay, Assalamu alaikum everyone. Welcome to this second session on artificial intelligence. All right, so it seems like it's a good time to make a start. Let us continue our discussion from where we left it off in the last class. All right, so to give you a small summary of what we did in the previous class, we looked at some of the definitions of artificial intelligence, and we also noted that there is no fixed or universally accepted definition of artificial intelligence. Reason being that the phenomena of intelligence itself is quite vague, and we have not been able to pin it down very precisely of what it exactly means by intelligence. And then we looked at some of the terms, including the levels of intelligent behavior, and we also saw what are some of the components of an artificial intelligence system. And we said that we can divide it into two parts, the engineering track and the theoretical track. In the engineering track, we actually build robots or machines that can move mechanically. That's the engineering track. But their movement is controlled by the program, by the software that is artificially intelligent. So that's the second track in AI, which is just a theoretical track in which we try to solve problems using computer science. Then we talked about a test that was devised in 1950 to determine whether we can say the machine is intelligent or not. As we just saw that it is actually a bit difficult to pin down an exact definition. So in order to avoid or circumvent this problem of defining artificial intelligence, a scientist named Alan Turing proposed a test in 1950. And the test was that you talk to the machine, and if you are able to determine that you are talking with the machine, then we say that the machine is not intelligent enough right now. But if the machine is intelligent enough to make you believe that you are actually having a conversation with a human counterpart, then we'll say that the machine is displaying some kind of intelligence. So in this direction, we saw that there were some attempts by people to write programs that can mimic conversation. And one of the earliest ones was ELIZA. ELIZA was written in 1966. And what you see on the screen is a sample dialogue between a human and this machine or this program called ELIZA. Now, ELIZA was trying to pretend to be a psychologist or psychiatrist. The human was trying to talk to this artificial psychologist. So the human input is given on this screen in lowercase, whereas the responses from ELIZA are in capital letters. So somebody types, then are all alike, right? So the response from the computer program was, in what way? So the person responds by writing or typing. They're always bragging about something or the other. And then ELIZA comes up with another response. Can you think of a specific example? And then the human says, well, my friend made me come here. And ELIZA said, oh, your friend made you come here, and so on and so on. So you can look at this, that it's sort of, in some sense, it makes kind of sense. Maybe we can think of situations where this can be a real conversation between people, but the restrictions of this program was that it can only pretend to be a psychologist. You cannot talk to ELIZA about any other topic. So it was programmed. And the way it worked was, the way we do it is that we parse the language, the input that is typed in by a human, we parse it and try to pick up some signals from them. For example, in the first sentence, men are all alike, ELIZA was able to understand that the statement is about some objects that are similar to each other, right? So the ELIZA program asks, in what way? So this is a pre-programmed response. Whenever there is a sentence in which some things are said to be similar to other, or some other adjectives are used, then this is the ready-made response. In what way? So the response from human is they are always bragging about something or other. So since over here in this sentence there was this keyword something, so Alisa picked up this one and wanted to have a specific example. And you can see that although it's not linked to the previous sentence in any way, it's only based on what you say in that sentence that Alisa generates its next response. But it sort of creates an impression that maybe it's a continuous conversation. So for example, in third line, a human says, well, my friend made me come here. So the technique over here is to just repeat what has been said, right? And just change my to your. So besides that, see the sentence is similar over here. So my has been changed to your, friend remains the same, made remains the same, and me is changed to you, obviously, and come here remains the same. So this is another technique. So Elisa was made up of many such techniques which would just examine the structure of the sentence, and from that use the ready-made response, right? So this was back in 1966. I would say quite impressive for that time. And then there was another program somewhat later, and it was when AI made a comeback, became more popular again, because as you know that AI was big thing in early 70s and early 80s, but then very soon people found out that it's very hard to write AI programs. So their interest went down, and during 90s and even 2000s, there was not much interest. But after 2010, interest in AI became more. Again, the AI became more and more popular. And these days, obviously, with the advent of social media and big data, AI has become very popular again. So this was somewhere around 2000, obviously, after a very long jump, like from 66 to 2000, almost 40 years later. But you can see that it has not progressed that much, right? So it's although it's much looks much more sophisticated if you read the responses from the chatbot, which is Eugene in this case. And Eugene is saying, "Hi, I hope you enjoy our conversation." And say, "So let's continue." And I forgot to ask you where you are from. And the person says, "I'm from Spain." And the bot is intelligent enough to say, "Hope it's a good place to live," and so on and so forth, right? So although there is some, you can see there is some advancement over here, but still the Turing test is still, I don't think this Eugene would be able to pass this test. So let me take you forward to an app that is available today. It's not a conversation app, but it's an app that produces text, right? So let me give you a demo of this over here. This is an app, and it does not like hold a conversation with you, but what it does is that it, if you type something, it will continue in that direction. So it's like kind of a story generation, automatic generation. So what I will ask you is to tell me a sentence to write here. So I'll type it in, and you'll see what the response comes from the computer. So can anyone tell me what should I type here?
Sir, what kind of a sentence?
Let's suppose you are writing your own diary, or you're writing a novel, for example, or you are writing an essay for some school report. It could be anything. So just give me the start of that thing. So just make up something that you are okay. When I start writing, I will write this, and I will type it in here. So give me a few sentences. Even more than one student can like help me over here. So you tell me one sentence, and the next sentence another student can tell me, and another student can tell me, and then see what happens. Give me a
Sir, take the sentence that I went outside the city last week.
I went outside the city last week. Very good. One more sentence, maybe. Anyone can chip in, like what should be another sentence over here?
And I saw a monkey.
And there I saw a monkey. Okay, good. So let's see how the computer will continue our story over here. I'll just press generate text over here, and let's see what comes here. So this text is being generated by computer now, right? Because you gave it a start, and the computer said, I have no idea how it got there, but there it was. The nearest we can go to a species whose numbers are plummeting, a Philippine bush monkey all by itself. I suppose it's possible that let's try to continue the sentence that the computer has stopped, right? So how would you finish this sentence? I suppose it's possible that let me type something. What should I type?
Person left him there.
Sorry? Suppose that
Person left him there.
person left it there, right? So let's ask the computer to continue the story. So you see, so it will keep on generating this text, and this text is being generated by an AI program. So there's no like human sitting on the other side. It's an AI program that looks at what we have written, and then it sort of tries to continue with what we are writing, right? So let's reset and let's start with another story. Can you give me another starting some very different context?
Sir, like me and my dad fought yesterday, or me and my dad argued yesterday.
Me and my dad argued yesterday, right? So if we ask the computer, so the computer is just making up a story, right? Based on the sentence that you have given it. So he said, I miss you, and I said, I miss
Sir,
you.
wow. Sir, this is just wow.
So this
I mean,
this is a demo of what AI is capable now today, right? So starting from Eliza, which was very rudimentary, then we saw Eugene, that was back in 2012, and now this is not conversation, but this is text generation, automatic text generation. So this is just another demo over here of artificial
Sir,
intelligence.
would it generate different result every time?
Yeah, of course. Every time you, even if the sentence is same, it will every time it will generate a new generate new text. So it's an interesting area. When I was experimenting with Eliza, there was another program called Poetry Generator, right? So what will happen is in that program, what it would do is you take a poem, right, in English, uh, and for example, it has 4 stanzas. So what the computer program would do is would take that poem and generate a new poem very similar to one that you have given me. So it would just change the nouns that are in there, change their adjectives, change the verbs. So in a poem, you normally know that each sentence has some kind of structure, right? The poet uses some metaphors, some analogies, and some verbs and adjectives. So we can just substitute them for other verbs and adjectives and other objects, and it would create a new poem. So sometimes it would really generate very interesting, meaningful poems rather than some random stuff. So that's also was back then. So these days, it's now possible to generate text using artificial intelligence. It's also possible to generate pictures, artificial pictures, right? Let me give you another demo of that, of how computers can generate very realistic looking pictures. And remember that these pictures are not like, it's not the computer is taking some picture and modifying it. You computer program, the AI program will just generate everything by itself. So there is no input given to the program. And this is also very interesting. Let me show you. Okay, so I'll start from here. So the painting that you see on the screen is actually created by AI.
Rectangular voids. Instead of clear edges, these buildings taper off and
So
bleed into
you
each
can
other,
see that
and their
it's
geometry
the
is
computer
obviously
is trying to
impossible.
transform
And I
this
think they're
painting as well.
floating
A GAN
As
might
the
have a solid
time goes
grasp on
by,
how something
let's
looks.
switch to
on
the
their
next
own.
example
I
over
think
here.
part of this comes down to their mastery of these really precise textures we're all familiar with. Sure, the buildings don't work, but their reflection onto the rainy street, the light polluted sky above and below, they're
For
There's one
aesthetic value
example here.
can be art.
Let me give you another example. So we must remember that these spaces are all completely generated by the computer itself. They're not like based on real photographs. They're just based on data and algorithms. All right, so these were some of the examples. Let me go back to my slides. So moving on, so let's look at the components of an artificial intelligence. And like we heard in the previous lecture, that one of the components is perception. Now, perception involves multiple type of sensors, but it also involves the input that you receive from your sensor, how to analyze it. And for artificial intelligence systems, two of the sensors are very important for analyzing their context. One is the image processing, well, all the input that's coming in from the cameras, you need to process those images, find out what's in that image so that the computer program can respond accordingly. And the second very important one is the microphone. That's also kind of a sensor. So all the input that is coming from the microphone, you need to analyze it, and that part is called as the language processing part. So we want our computers to listen to us and also able to understand what we are saying. So we need to analyze language. So in image analysis, what happens is that you take the image and you try to perform various operations on it. For example, you try to first identify where are the boundaries of the objects that are in this picture, right? And then try to distinguish one object from another. So, and the computer program decides, okay, in this picture, there are so many objects. And then the next step is to find out what is happening with those objects. For example, the computer program might determine, okay, there is a picture of a child here, and there's a picture of a park here, and the child is sitting on a swing. So the computer program will then try to put all these together and say, okay, in this scene, maybe the one child is playing in the playground, right? So it will infer from the relationship of the various objects that it has detected. It will try to detect what time it is, whether it's an indoor scene, an outdoor scene. So all this goes into image analysis. Something similar happens in language processing, right? So there are multiple levels because it's not possible to just, even if you are able to recognize what is being said. So before language processing comes a step called language recognition, or after that you have speech recognition, which means that if computer starts listening something, it will first try to guess or detect what is it, what kind of, what language is it hearing, right? Is it English or Urdu or Russian or some other language? And once the language has been detected, then speech recognition will try to recognize what are the words that are being said in that speech, right? So you need to identify each word and then put in a sentence. So once we get to that level, then we try to see what is the structure of this sentence, right? So in English, normally, if there is a sentence something like Bob kicked a ball, then we will see that there is an object, Bob, who's doing something, and there's an object which is a football over here, and there's a verb which is the kicking of the ball. So the syntax level, the one over here that you see, the syntax level, it just tries to identify where are the nouns, where are the verbs, where are adjectives, and how they all fit together. So it's just the structure of the sentence and finding out their parts and assigning them tags, whether this is a noun over here, it's an adjective over here, it's a verb over here, adverb over here, or what is it? So then we go to the next level, which is a semantic analysis, which is a level where we try to understand what is being said in that sentence. What is the meaning of that sentence? For example, the example I first gave you, that Bob kicked a ball, I can say the same thing by using a different sentence. For example, I can say, the football was kicked by a boy named Bob. Now, in this case, the structure of the sentence is quite different, right? I'm using different verbs. I'm using different order. The football comes first, and the verb is now in the past tense, and so on. But I'm trying to basically say the same thing, right? So the meaning of both the sentences are the same, although their syntactic structure is different, right? So once we know the syntactic structure, we know how many nouns, verbs are there and how they fit together, then we try to understand their meaning. What is the meaning of those sentences? But sometimes it's not possible to understand the meaning of the sentence if we don't know the context in which that sentence is being said. For example, the sentence, do you know what time it is it? Right? This is a sentence. We can all understand the meaning at the semantic level. At semantic level, somebody is inquiring what is the time right now, right? This is at the semantic level. But the context can really tell us what it actually means. For example, if somebody has been waiting for a long time, and then the friend shows up after a very long time, and so first friend is angry, and in his anger he asks his friend, "Do you know what time it is?" So that means that it's not that this friend wants to know what the time is, because he already knows what the time is. He's just trying to say that you are very late, right? So this is the contextual level in which we really understand what is being said. So at semantic level, it's just somebody is trying to find out what time it is, but at contextual level, it is actually you're telling somebody that you are quite late. So this happens a lot in language, right? So everything depends on the context. For example, if the sentence is, the bat fell on the ground, if the context is a cricket match, then obviously the bat means something else. But if it is like the context is a biologist exploring a cave and he saw a bat fell on the ground, so over there the bat would mean a different thing, right? It would be the creature that lives in the caves. So the semantic level, although in semantic level we know that the object or bat fell, this is the verb, on ground, we understand this is what happened, but the context will actually make it bring out the real meaning of the sentence, right? Because we need to know the context in which something is being said in order to understand its real meaning. So what happens is that there are computer programs that try to read something, for example, an essay written by a student, and then they try to apply all these levels of analysis. But sometimes it's easier if it's already known what the text is all about. For example, if the computer program, if I write a computer program that would extract information from ads for second-hand laptops. Suppose I have a long list of newspaper clips which are telling me, okay, this is an ad for a used laptop, and there's a lot of text in that advertisement. Although it's not a lot of text, but I think it's a small amount of text, because when you print an ad in a newspaper, it's usually a very small space that you have. So just a few lines, maybe 5 lines. And in those 5 lines, the seller is trying to describe their laptop, right? If the computer program wants to extract all the information from that advertisement. For example, the computer program wants to know what is the brand of this laptop they're selling, what is the price, what is the hard disk capacity, what is the screen size, etc., etc. So although the seller might have used terms like 256 or 10,000 or something, the computer program would not know whether this 256 is, are they talking about the RAM capacity, or they're talking about the price, or the hard disk capacity, or they're talking about the speed in gigahertz. What is 255, right? But if the computer program knows that the frame for this advert is the frame is an advertisement for used computers, so the computer would already know that it would be looking for this information, right? And then it will try to analyze what is being written in order to guess whether 256 means hard disk capacity or the speed. Or one way could be to see whether HDD appears next to 256 or MHS appears. So these kind of clues would be there. Sometimes they are called as heuristics. These are the techniques that are built into AI in order to help the computer program understand what is written in that text. And then there is another technique called semantic nets. It's more sophisticated than frames, because in this, what computer does is this tries to draw a graph in which the objects that it has discovered in the text, it tries to connect them together with kind of relationships. For example, over here, a sample sentence is Mary hit John, right? So the computer will try to extract all the information from this sentence by creating this semantic net. So you can see that in this semantic net, the computer has identified that Mary is a person, and Mary is the name of that person. Similarly, John is also a person, and John is the name of this person, and they are linked to each other with some action, right? And who is doing this action? The agent is doing this action, and from the sentence, the computer can understand that the agent in this case is Mary, because Mary is performing some action, and John is the object because the action is performed on John. So the computer program links this action to John by saying that John is the object of this action. And what is the action type? In this case, the computer knows that the hit is the action over here. So it could have been something else. For example, it was said, Mary gave a gift to John, or gave a greeting card to John, for example. So in that case, the action would be different. But in this case, although the computer knows that Mary has done something to John, over here it is that Mary has hit John, right? But if there were more information in the sentence, for example, if the sentence was Mary hit John with a pencil, then we would have more information. Okay, what kind of action was there? And then there are other links that computer has made, maybe from its past analysis of other sentences. For example, Alice is the parent of Mary, and David also parent of John, and both of them have their own date of birth, right? Mary was born on 8th May, and John was born on 12th June. So it as it like encounters new sentences, the computer will keep on building this semantic net until it can understand the whole situation. So now next I move to another very important concept. It's called the concept of production system. most of the AI programs that try to solve a particular problem, they work in a way that is very similar to this pattern. And this pattern, this abstract pattern, is called a production system. So production system is just a term that we apply to all those systems that have these three properties. The first property is that they should have a collection of states, right? Identifiable states. We can say, okay, the system is in this state, and we can also identify between some special states within the system. For example, we can say, okay, this is the start state of the whole system, or this is the final state of the system, or this is the intermediate state, or this is the desired state, right? We can label different states. And I'll explain what these states mean in my next slides. But the thing to remember over here is that in production system type of, in a production system is kind of a problem solving paradigm. In this paradigm, the system has states, and these states can have names. The second component that is common in all production systems is the collection of rules or moves. So these are also called as productions in the technical term, but these are rules through which you can make changes into the system. You can take a system from state 1 to state 2. And finally, the third component is the control system, and the control system decides what should be the next move, right? All this will become more clear if we look at example of a chess game, or maybe some other game. Let me give you an example. Okay, so this example is this 8 puzzle that we saw before. Now this is a production system. Why is it a production system? Because it's a typical way an AI system, artificial intelligence system, tries to solve problems, right? So let's see whether we can identify the 3 components in the previous slide. In this example, the 3 components are collection of states, collection of rules, and the control system. So what are these states? Now, what you see on the screen is just one state of this system. And if I move this tile down, the 5 tile down, right? I can move it down over here. So then in that case, 5 would be here, and this would be an empty vacant slot over here. So that would be a new state of the system. Right? So state means how different pieces are at a particular situation, or what is their value. So what is the state of the system? So this is one state. It could have many states, right? When we keep on moving the tiles, the system will go from one state to another state to another state. It will keep on going into many states. And you will realize very quickly that there is one state that is our desired state in this game, right? The desired state is that all tiles are ordered in the proper sequence. That is the desired state, right? Now, you'll also recognize the second component of the production system here, which is called as the rules of the game. So the rules of the game is that all tiles can be, you can slide them down or up or left or right, provided there is a vacant slot available next to them, right? So these, the moves, although all tiles can move in all directions, but at a specific state, they are constrained. Each state puts a constraint on the tiles. For example, this state has put constraints on tile number 1, 4, 7, and 3 and 8, right? Only 3 tiles are free to move. Tile number 5 is free to move, tile number 2 is free to move, and tile number 6 is also free to move. But they are not free to move in all directions. And number 5 is only allowed to move down, and 2 is only allowed to move right, and 6 is only allowed to move up. But if you suppose that this vacancy was here in the middle, right? And the 5 was its own place, and over here it was 2 rather than 5, right? And this was in the center, it was an empty space. Then this state would have allowed tile number 3, 4, 8, and 2 to move, right? And each would move in would be able to move in a different direction depending on this state. So we see that in this system, we have a system that have multiple states. So that's property number 1. And these states can have like their names, for example, the starting state or the desired state. These are specific states that have their own names. That's the first component or first property of production system. The second component or second property is that there are ways in which we change the state of the system. In this case, we change the state of the system by sliding tiles. We can slide them up, down, left, or right. But we cannot move these tiles very freely. The movements that are allowed are actually constrained by the state. So every state will permit certain moves to be made, but it will disallow certain other moves to be made. And this is common with all production systems. For example, if we were talking about the game of chess, you'll see that every board position is the state of that system. And in each state, the pieces are free to move, but they are also constraints. There are certain constraints. Similarly, if we are talking about RoboCup and or a real football game, then you can see that it has a lot of states, right? Each state means where each player is at that particular moment, where the ball is at that particular moment. So that defines the new state of the game, right? And at each state, you can go from one state to the next state, but only through allowed moves. For example, running is one move in football game which is allowed, which takes you to the next state, right? And there are certain states that are desired state. For example, making goals against the opponent, that is a desired state, one of the desired state. And the final desired state is winning the game. And then the third component or third property is called as a control system. The control system is the system that decides which move shall be made next. What should be the next move, right? So in this case, for example, what you're seeing on the screen, the control system has 3 choices. It can either move the tile 5 down, or it can move the tile 6 up, or it can move tile 2 to the right. So what move is the best move? Which of these moves is the best move? That is the task of the control system to decide, which means the AI reasoning part of AI, the program that will do the reasoning. And how will that program perform its reasoning? It will perform its reasoning by comparing the new states. So for example, if it slides down tile number 5, the system will come into new state. And then the computer will ask, is this new state closer to my desired state? Desired state is when all the tiles are in sequence, in right sequence, right? So it's the goal-seeking behavior that we are talking about, that we also discussed in our previous class. So since the computer program, the reasoning part of this computer program knows what is the desired state, it will evaluate each move against that desired state. How how easily this move will take the system to the desired state, or how quickly it will take the system to the desired state. And then based on that estimate, it will decide, okay, which move should be the best move at this point. So let's look at what actually happens when the computer is trying to solve this problem. So what it will do, the computer program, it will first of all make something known as a state graph. And then it will search through that graph using something known as search tree. So I'll show you both of them. So this, what you see now, is called the state graph. So it's the state graph of that same puzzle. So for example, we could be, for example, we might be over here. This, we might start, when we start, let's suppose we found the puzzle to be in this state, right? Now from here, you can see the system can go into 4 different states. If I move 2 down, I will go into a new state. If I move 4 over here, it will a new state, and 5 will cause a new state, 6 will cause a new state. So you see that this state that you see over here is achieved when we move 5 up over here. When we move 5 up, we get an empty slot here, and 5 is now in the place of empty slot, right? So the state has changed by sliding tile number 5. This could be, for example, the state when we move slide tile 2. This could be the state when we move the tile 6, and this could be when we move the tile 4. Although in the diagram, I've not shown all the tiles, they are just gray boxes, but you can imagine that these are all tiles over here, right? And this is a different state. And from this state, you can either go back to this previous state by pushing 5 down. If you push 5 down from this state, you will go back to this state with this arrow, right? But if you move 8 into this vacant block, then you will move into this goal state, which is the desired state, because the computer will recognize that now all the tiles are in sequence, 1, 2, 3, 4, 5, 6, 7, 8. On the other hand, if you, instead of moving 8, if you move 7, you will come to this state, right? And from here, you know that there are only two moves possible. Either you can push 4 down, or you can move 7 over here. So if you move 7 over here, you will go back to this state, right? Because over here 7 was at the bottom left corner. So if you move this 7 over here, you will go back to this state. But if you move 4 down, you will go to this state over here, right? So each state will have different possibilities, right? Either there is just 2 possibilities, or there may be 3 possibilities or 4 possibilities. So in this case, you can see that on the screen that if you are in this goal state, there are only 2 possibilities. Either you can bring 6 down, or you can move 8 across, right? So if you move 6 down, you will come to this state, or 6 is down, and there's an empty box over here. But if you move 8 to right, then you'll go back to this state where 8 is in the bottom right corner, and the empty space is over here where the 8 was. But from this state, this one, you have 3 possibilities, right? Because there are 3 moves possible. You can either move 5 down, or you can move 7, or you can move 8. So all these 3 moves will take you to 3 new states, right? This one state is shown over here, another is shown over here, the third one is over here, right? But when you are in this state, for example, there are four options in this state. Like either you can bring 2 down, or 4 to right, or 5 to left, or you can bring 8 up. And these all will lead to different states. So when you complete this picture from all states to all other possible states, you will say that you have created the uh, state graph of the puzzle, right? So in the end, when you count all these boxes or these states, you'll know that puzzle 8 game can have these many states. There might be many such. I don't know the exact number, what would the exact number, but if you complete this graph, then you will be able to count how many states are possible. So when you are given a new puzzle in your hand, you can look at it and see, okay, I'm in this state, and now I have to go to the goal state, right? Suppose you found yourself in this corner, and you want to be here. This is the desired state, and this is your initial state, starting state. Then you know you'll have to come down like this and not go in other directions like this, right? So this is the task of the control system to make these choices. And the control system can make these choices because the computer system has made the state graph, and it knows where the goal state is. And it does it by performing a search operation. In the next slide, I'll show you how the search operation is performed. So in this diagram, this is a search tree. The search tree is, it starts with a given state. For example, this was the initial state. Right? This is just a randomly selected initial state in which the tiles were like 1, 3, 5, 4, 2, 7, 8, 6. So they're all very much jumbled up. But from this state, the computer knows that there are only 3 possibilities, right? You can go either over here or over here or here. So you can very easily see that the three possibilities or 3 new states will come into being if you make these 3 moves. If you move 5 down, you will come to this state. Okay, this is a state where you moved 5 down. If you move 2 to the right, you will come to this state. And if you move 6 up, you will come to this state over here, where the 6 has been moved up. And from each of these new 3 states, see, there are other possibilities. So from this state, you can either go back to the top, or you can enter a new state in which you move 8 over here, right? So you can see that 8 has been moved over here. Now the gap is in the middle. And then again, you have 2 options over here. In the middle, you have 3 options. And again, at the bottom, you have 1 option to go down, 1 option to go back. And then you continue this with this tree. Tree is that how these states are linked together, right? And you know that the goal state is over here. This is the goal state, where all the tiles are in sequence. In all other states, you'll see that the tiles are jumbled up. They are not the desired state. So if the computer finds itself over here, it will search through this tree and it will establish a path, right? So how it will search, there are 2 methods it can use to search. One is called as the depth first approach. And the second one is called the breadth first. In the depth first, what happens is that you decide on a side, let's say left side, and then you keep on going as far down as you can, keeping to the left. And when you hit the bottom, then you go back up, and then you start the process again. So if I, for example, use the depth first approach and left preference, then I will go to this state first, and then obviously I'll go down because this is the depth first approach. Now over here again, I have 2 options. I can go either left or right, but I know that I will always take the left side, right? So I'll come here, then I'll come down, again, I have two options. I will take the left option, and over here I'll find out, okay, I have reached the bottom of this tree here. So when I've reached the bottom of the tree, then I will go up and take the right option, right? And again, I will find myself at the bottom. So I will start going back up. I know I have already come to this point, so I'll go further up. I know I've already come to this point, so I'll go further up. I know I've already come to this point. So now I have this option of either going up or going down. But the algorithm says that I have to go down first rather than up first, right? So I'll go down. Again, I'll have two options, but going left or right, I'll take the leftmost option because this is a fixed one. And then I'll come down again here and then take the left one, and I'll hit the bottom. I'll go back up. Again, I have an option to come down, so I'll come down over here. I'll come here. I'll hit the rock bottom. Then I'll go back up, and come over here. Now, again, I have two options to go down, right? I don't want to go up because there are two options that are taking me down. So if there are two options to take me down, I take the one that is left. So this is the left one. So I come here, I go down again using the left approach, hit the bottom, and then go back up, come down, and so on and so forth. So this way, this search technique is called the depth first technique. So in this way, I'll go from, I will cover all the states in the tree. And once I have found out like that in order to reach the goal state, the shortest path is this one, right? So whenever I encounter this state, the computer will automatically know that this is the path to take to reach the final state and goal in the shortest possible time. So I won't make other moves. So this is how the control system will decide which move to take next. It will first construct a search tree using all the states, and then it will traverse the tree, and it will stop as soon as it finds the goal state. And then it will say, okay, this is the best way to solve this particular problem. So this particular technique that I've told you today, that you treat every problem as a production system, and then in the production system, you find out what are the possible states of this system, and then you find out what are the possible moves at each state, and then you construct a control system which will perform this search, and this search will actually allow it to reach the desired state in the best possible manner, and will say this is the task that the control system has performed. Or we can, in other words, say that the control system has made these choices, or control system has employed this reasoning in order to get to the final state. So this is something about how production systems work in artificial intelligence. We'll revise them in our next class as well in order to consolidate our learning with some more examples. But that's all for today from my side. If you have any questions, thank you very much.